for the rest of my life, I want to reflect on what light is.
Yeah.
Einstein, right? I mean, who can blame him? Light is like this everyday miracle we just totally take for granted. And we are about to take a deep dive, get this, into your stack of physics and engineering docs on optical radiation.
Yeah.
Heavy stuff. But trust me, buried in all those equations and, technical jargon,
Yeah.
there are some seriously mind-blowing insights about the light we live with every single day.
And you know what? Even if you're not designing the next LED revolution or anything,
Right.
understanding how light actually works, it really matters. Think of it like this. You wouldn't bake a cake without knowing how the ingredients work together.
True.
Right. Lighting's the same way.
That's a good analogy.
Mhm.
And what's so wild to me is how quickly things get complicated. We say light like it's this simple thing, but then these documents, they call it optical radiation.
Mm-hmm.
It's is there a difference? Apparently, even Newton was puzzled by how we actually experience light, not just the science of it.
Oh, absolutely. And it's a question that scientists have been wrestling with for centuries, Is light a wave, like you think about a ripple in a pond, or is it a stream of particles, like these tiny little bullets of energy? It's this classic wave-particle duality. And the funny thing is, even today, both models are considered valid.
Okay, now my head is officially spinning.
Okay.
So how do these documents, how do they want us to think about light? Or, I guess, optical radiation?
Well, they actually lay out 4 different ways of looking at it, each one more complex than the last. So we've got quantum optics, which is diving into the nitty-gritty of those tiny little photons we talked about.
Okay.
That's the particle side of things.
Okay.
And this model is really useful for understanding how LEDs work, for example.
Got it.
Then you've got physical optics, which deals with electromagnetic waves.
Okay.
And this helps us understand how light sources in general behave.
Okay, so we've got the super tiny world of photons and then something a little bit bigger with the waves. But for someone like me who's, maybe more interested in how light actually works in a room, which model should I be picturing in my head?
You'd be most at home with geometric optics.
Yep.
This is where things get really practical. We're talking about rays of light, how they bounce off surfaces, that's reflection,
Right.
how they bend when they pass through different materials, refraction, all that good stuff.
Right.
It's the model that really helps you visualize what light is actually doing in a space.
Got it. Okay, that's starting to make more sense. And then there's radiative transfer.
Yeah.
What's that all about?
That's where we zoom out even further. We look at the overall movement of light energy, think beams of light and how much power they carry.
Okay.
This model helps us understand things like how bright a light source appears, how evenly it illuminates a space, that sort of thing. Really all about what you actually experience.
So it's the difference between knowing the recipe of a cake and actually tasting how sweet it is.
Exactly.
Wow.
But here's where it gets really, really interesting.
Okay.
Remember that term pointing vector we saw earlier?
Yeah.
Basically, it's a vector that shows us the direction and strength of electromagnetic energy flow. And guess what?
What?
This vector is directly related to how bright we perceive light to be.
Wait, so you're saying that 2 light bulbs with the same wattage, they could actually look drastically different in terms of brightness?
You got it. It all comes down to how focused or spread out the light is. That's why a focused spotlight can feel blinding even at low wattage, while a diffuse light source might feel much gentler even if it's technically using more power.
Wow, okay. Mind blown.
Right.
But let's back up for a second.
Okay.
We've been talking about models and vectors. But how do we obviously go from, say, flipping a switch to seeing actual light? I see something in here about incandescent light. Is that your good old-fashioned light bulb?
You guessed it. Incandescent light, it's all about heat.
Okay.
Think about what happens when you heat a piece of metal. It starts to glow, right?
Right.
That's incandescence. Basically, you're pumping energy into the atoms of that metal filament, causing their electrons to get all excited, and they jump to higher energy levels. And when they fall back down to their normal state, they release that extra energy as light.
So that warm, inviting glow we associate with old-fashioned light bulbs is actually just excited electrons calming down.
Exactly.
That's amazing.
And you know what? The hotter the filament gets, the more energy is released, and the brighter the light appears.
That makes sense. But how come not all light bulbs look the same when they light up?
That's because different materials and temperatures, they produce different wavelengths of light, which we perceive as different colors.
Yeah.
And that's where the concept of a black body radiator comes in.
A black body radiator. Okay, that sounds kind of ominous. Like a black hole's less glamorous cousin or something.
Uh-huh. not quite. It's actually a theoretical object. It absorbs all light and reflects none, hence the name black.
Yeah.
But here's why it matters. A black body radiator, it emits light based solely on its temperature, which makes it like the perfect yardstick for comparing other light sources.
So it's like the gold standard of light emitters. Why is that so important?
You got it. It lets us define things like spectral emissivity, that basically tells us how much light a real-world source emits at each wavelength compared to that, like, ideal black body.
So we can look at, say, a fluorescent tube and be like, this is this close to that perfect light, scientifically.
Exactly.
That's pretty neat. But before we dive into all the different light sources, let's talk about how we actually describe or measure something as subjective as whiteness. I mean, what looks warm white to me might look a bit yellowish to someone else, you know?
Absolutely. And that's something, lighting experts have been grappling with for ages. One tool we use is correlated color temperature, or CCT. Remember how we were talking about the black body radiator changing color as it heats up?
Yeah, it went from like reddish to orange to yellow, then white, and eventually even bluish white at like super high temperatures, right?
Exactly. So CCT uses that principle. We take the temperature of the black body that most closely matches the appearance of a light source,
Okay.
and we use that to describe its whiteness.
So a lower CCT would be like your cozy incandescent bulb, and a higher CCT would be more like daylight.
Spot on. And you'll often see CCT values on, light bulb packaging, 2700K for a warm white, 4000K for a cool white, and so on.
Okay, that makes sense. But is CCT the whole story when it comes to describing how light makes things look? These documents also mention the CIE Color Rendering Index. What's that all about?
That's another key piece of the puzzle. CRI is a way to measure how accurately colors appear under a given light source compared to a reference light source.
Okay.
Usually that trusty black body radiator again, or daylight. So the higher the CRI, the more true colors appear.
So a light source with a high CRI would make a red apple look, well, like a real red apple, not some weird washed out shade of red.
Exactly. A perfect score is 100, meaning the light source renders colors exactly like the reference source.
Wow.
But even sources with CRI values in the 80s or 90s are considered pretty good for most applications.
That's good to know. But I have a feeling there's more to the story.
Yeah.
I saw something about like the limitations of CRI and these new metrics being developed. It's like there's the scientific measurement, and then there's how we actually perceive color. What looks good to us versus what a chart says. How do we make sense of that gap?
You hit on a really crucial point. CRI, it does have its weaknesses. For one, it's based on a limited set of test color samples. So it might not tell the whole story about how a light source renders all colors. And as you said, it doesn't fully capture those nuances of human perception.
Right, like a museum might want lighting that makes its artifacts look like historically accurate, even if it's not the most flattering. But in a clothing store, you'd probably want lighting that makes people look their best.
Right, exactly. And that's where those newer metrics come in.
Okay.
One promising development is color appearance models, or CAMs. These models try to factor in things like surrounding colors, how our eyes adapt to different lighting, even cultural preferences.
Wow.
They're a lot more sophisticated than just a single CRI number.
So it's like saying, okay, CRI gives us a basic idea, but to really nail the lighting, we need to consider the whole picture. The environment, the person looking at things, maybe even their mood.
Precisely. And there's a great example in these documents about supermarkets.
Okay.
They use different lighting for different displays. Warmer light on meat to make it look fresher, cooler light on produce to emphasize those, vibrant greens. They're using light to, subtly nudge our perceptions, even to influence our choices.
That's fascinating. It shows just how powerful light can be, going way beyond just illumination. Speaking of which, I'm curious about this concept of gamut area. I saw it mentioned in the context of color. What is that exactly?
So gamut area is that like saying some light sources make colors seem like richer and more intense compared to others.
That's a great way to put it. Yeah, gamut area essentially measures that colorfulness or vibrancy that we perceive from a light source.
Okay.
It's calculated by plotting the color coordinates of those test color samples we talked about under a given light source.
Right.
The larger the area they cover, the bigger the gamut area. And generally, the more colorful things appear.
So it's like some light sources have more colors in their toolbox, so to speak.
Exactly. And just like with CCT and CRI, designers can use gamut area to really fine-tune the mood of a space. Want a vibrant, energetic atmosphere? Choose a light source with a large gamut area. Need something more calming and subdued. A smaller gamut area might be a better fit. It's amazing how much thought goes into something as seemingly simple as choosing a light bulb.
Right. But it goes even deeper than that.
Okay.
There's growing evidence suggesting a link between gamut area and visual clarity.
Wait, really? You mean the colorfulness of light can actually affect how clearly we see things?
You got it. There's research indicating that people actually prefer lower light levels in spaces lit with larger gamut area light sources because they perceive the same level of detail as they would with higher light levels from a smaller gamut area source. It's like those vibrant colors are tricking our brains into thinking things are brighter and sharper than they actually are.
That is so cool. So not only can light impact our mood and perception of color, it can actually change how clearly we see. I'm starting to think light is a lot sneakier than I gave it credit for.
It really is. But as with everything in lighting, it's this complex interplay of factors. There's still so much we're learning about how it all works. But what's clear is that there's often a difference between how the lighting industry defines good lighting based on things like CRI and what people actually find visually appealing.
It's like that idea of a flattery index that was mentioned in these documents. People want lighting that makes them and their surroundings, I guess, look good, which isn't always the same as like perfect color accuracy.
Exactly.
It's like choosing the right filter for a photo.
Exactly. It goes back to that supermarket example.
Right.
They're not picking lights based on, cold, hard CRI numbers. They're choosing based on what makes their produce look its most enticing, their meats their freshest. It's about creating an experience, not just illuminating a space.
It sounds like there's a real art to lighting design, a blend of like scientific understanding and aesthetic sensibility.
Absolutely. And that's why it's so important to pay attention to how light makes you feel. Think about a space where you feel truly comfortable and visually at ease. What role does the lighting play in that feeling? Is it the warmth of the color temperature, the vibrancy of the colors, or something else entirely?
That's a great point to end on, I think. We often take light for granted, but it plays such a huge role in how we experience the world.
Right.
So next time you walk into a room, take a moment to appreciate the light. You might be surprised by what you discover.
I completely agree. Light is full of surprises, and the more we learn about it, honestly, the more fascinating it becomes.